Hello, everyone. Today we continue to talk about another time-weighted control chart, EWMA. And then I'm going to introduce Monte Carlo method for finding run length distribution for time-weighted control chart. EWMA stands for exponentially weighted moving average. The EWMA statistic is the weighted average of observation xi, and previous EWMA statistic zi minus 1. Then why this is called exponentially weighted moving average? After some computations, you can see zi is a weighted moving average of the past data of xi minus j, with the weight being 1 minus lambda power 2 j. This weight decreases exponentially as one goes back in time. So we call it exponentially weighted. We need to determine control limit for an EWMA chart. Because xi is assumed to follow a normal distribution, its weighted average zi also follows normal distribution. From the previous lecture, we learned that if we know the mean and variance of zi, we can build control chart by applying the general control chart model. Then we need to compute the mean and variance of zi. I'm going to skip details, but the expectation of zi converges to mu as I goes to infinity. If mu equal to mu0, then we can say that expectation zi converges to mu0. Similarly, variance of zi can be obtained after some computations. Note that the variance of zi depends on the time index I, and it goes to sigma squared times lambda divided by 2 minus lambda as I goes to infinity. We call this value the steady state value. Based on expectation of zi and variance of zi, we can construct the EWMA control chart using the global control chart model as shown in this slide. Consequently, there are two versions, time varying control limit and steady state control limit. And let's apply EWMA to the same example. As the table shows, zi values are computed for 30 observations. Here we use lambda equal to 0.1 and L equal to 2.7 to compute control limit. The results show that a mean shift in the process was detected at 29th observation, which is the same result as the QSUM chart. This figure shows the EWMA chart and its time varying control limit. Unlike other control chart we have learned, EWMA has time varying control limit. We can see they eventually converge to the steady state values, which are 10.62 for upper control limit and 9.38 for lower control limit in this example. We need to determine parameters to design the EWMA chart. EWMA requires two parameters, lambda and L. The lambda controls how much memory the chart has. If lambda equal to 1, then EWMA equals to the short control chart. The larger lambda indicates short memory, and it is good for detecting large changes, while small lambda indicates long memory, and it is good for detecting small changes. Typical choice for lambda is between 0.05 and 0.25. Generally, L equal to 3, but for lambda less than 0.1, 2.6 to 2.8 is a popular choice. More general approach relies on the impact of lambda and L combination on the ARL. Similar to the QSUM chart, there are two approaches to design the EWMA chart, relying on results from literature and simulations. This table provides the result of ARL for various combinations of lambda and L to make ARL 0 to be 500. For the specific shift in mean, we can choose proper combinations of lambda and L to obtain the desired or required ARL1. For example, if we choose lambda 0.1 and L 2.814, then for 1 sigma mean shift, we can expect ARL 0, 500, and ARL 1 to be 10.3 on average. In this way, we can find out the QSUM chart that yields similar performance in terms of ARL 0 and ARL 1. The corresponding QSUM chart design would be K equal to 0.5 and H equal to 5. Before we move on, new topic about simulation-based method for finding run length distribution. Let's wrap up the EWMA chart. We consider the individual observation for EWMA chart, that is n equal to 1. The EWMA chart can be applied to a sample mean by replacing xi and sigma by the corresponding sample statistics. Then the formula for control limits changes accordingly. As another approach to design a control chart, let me introduce the simulation-based approach. As we learned in a previous lesson, the short control chart provides an analytical way to compute ARL 0 and ARL 1. However, for most of detection method, including the QSUM and EWMA chart, run length distribution are difficult to calculate analytically. For such complicated detection method, Monte Carlo simulation methods were developed to approximate run length distributions and compute the ARLs. Here, let me explain the simulation-based procedure in 5 steps for finding run length distribution. First, generate a trial of long sequence of observation using a random number generator with the assumed distribution. Most of the time, we use normal distribution. Second, implement the chart on the generated sequence from the first step. Third, when the chart signals the first time, record the run length for that sequence. Fourth, we repeat step 1 through step 3 n times. N should be a large number, so each time generate a new sequence. Fifth, as a result, we can obtain n values of run lengths, and we can estimate the ARL using them. So here is an example of our code to simulate run lengths and to estimate the ARL. In this example, we generate sequence having 5,000 observations and apply the QSUM chart to detect the first signal. We repeat this procedure 10,000 times. This graph is the histogram of the run lengths. Their average is 168.1932, which is the estimated ARL of the QSUM chart with H equal to 4 and K equal to 0.5 and sigma equal to 1. For different combinations of parameters, we just changed the settings for the QSUM chart in the code. Then we can compute the corresponding ARL using the simulation-based method. Let me wrap up the Monte Carlo method. The Monte Carlo method works in principle for any kind of control chart. The major shortcoming is its high, sometimes unaffordable computation demand. The sequence length and the size of repetition should be large enough numbers. Okay, let me summarize a time-weighted control chart. Today we talked about two time-weighted control chart and the way to design them. To design such control chart, unlike the short control chart, we need to rely on ARL, which can be obtained either result from literature or simulation-based method. For estimating ARL using simulation, we can use the Monte Carlo method. Thank you.